All right, so summary of lecture 7. Let me start with a bigger picture summary. So what did we do? In the first part of the course, we did renormalized perturbation theory, right? So we renormalized QED as an example at one loop. We saw the mechanism, how it was working, right? The starting point was that you would start with the bare Lagrangian, then you would introduce to each field, you would introduce to every field phi I, you would introduce, so this is the bare, you would introduce some renormalized fields, right? And then a corresponding wave function renormalization. Then you would write down the bare Lagrangian in terms of a renormalized one with renormalized couplings as well, right? And then whatever was the difference would be called the counterterms, right? Then we would do a calculation, say at one loop, we would set renormalization conditions to build a dictionary between bare variables and the observed variables, right? That would fix for you these the coefficients of the counterterm. So we package these delta z's in terms of these zi's and grs, the differences between them in terms of a bunch of delta z's and delta g's, right? And the knowledge of these that we find once we solve for, when we set the renormalization condition, will renormalize the theory at one loop. That means that once you have the dictionary, then you just go ahead and do a calculation at one loop. Your favorite diagram, you have a dictionary, so you can express everything in terms of the physical variables. Of course, these one loop intervals were divergent, so these guys are formally speaking infinite. At the moment, we have not discussed what is the origin of this infinity. It's actually very physical. It took renormalization group to realize. So Dirac famously, when they came up with this story, they said in quantum field theory, we push all infinities under the rug. So it made no sense that you're doing perturbation theory with infinite, where things diverge. It took Wilson, Kadanoff, and their ideas of renormalization motivated from lattice models to actually to explain what this is. So we're going to explain that, right? For now, I just wanted you guys to see how it works in practice, right? Then that was renormalized perturbation theory, right? Yeah, so the way we dealt with this was using DIMREG, right? We did DIMREG. Then I switched gears a little bit and started talking about effective actions, right? And effective action, what was the point of effective action? Well, I'm just going to review it now. So we introduced effective actions in the previous lecture. So I'm gonna, are there any questions about part one? Because today, a lot of what I'm gonna say is going to be, well, actually going forward, it's all gonna be relying on this. We're gonna be trying to, first, I'll tell you a little bit about some magical things here. The connection between renormalization and symmetry, we're gonna discuss that. That's gonna be the theme for the rest of this. Actually, symmetry is actually our most powerful tool in building quantum field theory models. Anyway. So we're going to discuss that. But before I go ahead, are there any questions?
Maybe I missed it at some point, or we didn't touch on it, but for renormalization group, which part of this process, or what is the group structure in renormalization?
It's a misnomer. Okay. There is there's no, if you're asking as a in a mathematical sense where there is a group structure, there simply isn't. At least in full generality.
It should be a semi-group.
In a lot of cases, but not always. So we'll discuss that. I'll discuss, but you're absolutely right about the fact that there is something that resembles semi-group. Some might say there's a group structure sometimes, and that those classical models are of interest. When we do exact RG, that's the closest we come to group structure. But anyway, that doesn't. We're not there yet.
Are the elements, are any of these like the elements of that group, or have we not even gotten to that?
We will not get there. Yeah, you'll see. You're gonna learn about a normalization group, and you're not gonna see obviously in this course any group in it, or later on. All right. Any other questions? I actually wonder what is the origin of the word renormalization group. All right. All right. So last time, what did we discuss? We started by discussing some two-loop diagrams in Lambda 5-4 theory. I picked particularly simple diagrams, right? In particular, because I just want to establish, to communicate to you guys, what is the structure of divergence at higher loop, right? So for example, in QED, what we saw that was the structure of divergences were log divergences. There were log divergences in one loop, and that was very important. How does log divergence show itself in dim-reg? 1 over epsilon, or epsilon bar if you use the conventional MMS bar scheme. Now, then what we saw was that at two loop, okay, so I'm going to discuss that. So the point of this was to give you an idea of how the structure. So at two loop, we looked at the corrections to the propagator. So what are for lambda 5-4 at two loop, what should I be discussing? What are the two diagrams that I have to be looking at corrections to? Now, what are the two correlators, a diagram? What are the two correlators I should be looking at corrections to? And what's that? 2-point function, propagator, right? What else? Vertex. The 5-4. Those are the only things I have, right? So what we focused on last time was just the propagator, right? So the vertex is a little bit more complicated, and I just want to, you could learn about a bunch of calculations of that. You could see explicit examples of it and Peskin. But so lambda 5-4, if you look at the two loop contributions, there's this diagram to propagator, and then there's this diagram, right? But then we are doing renormalized perturbation theory, so there's this diagram as well. Because this this thing is these are things that are coming from the, like if you recall in Feynman diagrams, there were these terms, right? That have to do with delta M and delta Z, right? So now when we solve that one loop for this counter term, this was order lambda, right? How do I see this is order lambda at one loop? Because its job, its raison d'etre, is to cancel this diagram, divergence of this diagram. And this diagram is order lambda, therefore it has to be lambda, right? That's what it achieves under renormalization condition, right? The renormalization condition tells you that this guy and that guy at your mass scale of interest cancel, right? So if this is order lambda, that's going to be order lambda, right? So now this diagram is clear. This diagram is of course order lambda squared, right? And so is this diagram, right? Now, what other diagrams we have? We had this guy. We saw that these two guys cancel. That's not surprising. It's almost obvious that they cancel. I don't know if you can see that, but this is very crude. This is not a rigorous statement, but roughly speaking, you can see that. The diagram here, right, looks like the diagram here. Up here looks like these guys are canceling. This is not an argument, right? There's a long story. These type of arguments observations are turned into rigorous arguments to prove that the inclusion, once your theory is normalizable, you using local counterterms, this MHC theorem I coded, right? You could capture all of them to all orders. We actually had a student give a journal club about this last year, how this proof works. Then for the propagator at two loop, there's also this diagram, right? Now you have this guy and this guy. These are the guys that cancel this. Now, what was very interesting here was that for this, you had to, because this ordered lambda squared, you needed this to have a lambda squared term, right? So your delta, you expand in fully non-perturbatively, you expand your delta and Z and M in terms of lambda, right? So there is a first order term What was the first order term for delta Z? Huh?
Was it delta Z?
Correct. That's zero. So this was absent. There's potential lambda squared term, right? But I don't need to worry about that in this diagram because of just counting of the orders of lambda, right? The lambda squared term of this piece will come into play to cancel this. Good? Is it clear? Also, this guy, the lambda squared piece of it will come in. All right. And why do I not have to worry about something like this? Why do I never draw a diagram like this? Exactly, it's not 1PI, right? It's not 1PI. That's the beauty of this story of 1PI, right? The number of diagrams, when the part that has to do from going from the full propagator to 1PI, you could do explicitly. You could resum those guys, and then the 1PI is like a lot less diagrams. It's still an insane number as you go to higher loops, but all right. So this is this is what we saw. We discussed. We said that at higher loop. So of course. So what was the divergence order of these guys? Lambda squared, right? Now, well, sorry, I'm lying. Is lambda squared log lambda squared, right? Because you had two integrals. One of them was k1, the other one was k2, right? There are three propagators and two integrals. Good. There are three propagators, two integrals. Now the one integral over p captures one propagator. That gives you lambda squared divergence. And then because the integral over p and k is separate. Right? The structure of the diagram is like, and then the other guy will give you log divergence. Just by as a sort of almost follows from the Legos of Feynman diagrams, that diagram like this squares blows up like lambda squared, log of lambda squared to the power of n minus 1 by the argument that I just told you, right? Now, for vertex, similar arguments work. You could just, like you just write down the integral structure. Good? So we discussed some of that, but now then we completely switched gears and we started talking about the connection between statistical field theory, and we went back to the connection between statistical field theory and quantum field theory. So here's the connection. In the QFD, you have a field which is phi of x mu, right? In classical finite temperature physics, your corresponding field is the magnetization. I gave you this argument, right? So what is magnetization? Your UV degrees of freedom are these these spins. You average them. Spins are of course up and down, but when you average a lot of them within a block, that becomes almost continuous, right? And now your field has to be smooth, which means that the averages from one block to the next block have to change very slowly. That is the continuum limit. It's a limit that's very hard to make precise, but anyway. But magnetization, m of x, plays the role of phi of x mu. The source jx, here the analog of it is b of x, right? Because once you turn on a magnetic field, m responds, right? That's called linear response, actually. And so does linear is the first order. J of x is coupled to, is a source for phi of x, right? Here, what is the origin of fluctuation? We talked about this, right? Fluctuations have to do with, fluctuations is what you need to define quantum field, to define field theory, right? Quantum field theory. So here, the origin of fluctuations are thermal fluctuations, right? Whereas here, the quantum fluctuations are controlled not by 1 over h bar, but they're controlled by h bar. Good? Now, in the StatMech side, what you have is a partition function that in the continuum limit is the path integral over magnetization, e to minus beta h, plus integral of b of m. Right? This is a source, this is external source, this is magnetization. So what is the role of beta here? Beta is dimension full, right? It's inverse temperature. What's the role of beta? Yeah, but like, what does beta sit next to? Hamiltonian. Hamiltonian is energy. So beta has units of time, right? It sets the unit of clock, time, for your Hamiltonian. This is an important lesson in physics, right? This is a very important lesson in physics. What does Hamiltonian sit next to? E to the power of IHT, right? So how do you know, like, what is, like T is dimension full? So so is Hamiltonian. They have inverse dimensions. So if you pick units for time or units for Hamiltonian, they're the same thing, right? So it's like picking your unit clock, unit of time. Importantly here, there's no H bar. Hopefully that's clear. H is dimension full. You're interested in exponentiating something that has H in it. Beta's role is to set the unit of time. Set the units of our Hamiltonian, normalization of Hamiltonian, right? Now, similarly, here you have Z of J, right? Integral of d phi j e to minus s phi plus integral of j o. But S, if you recall, has dimensions. Action has dimensions. What's the dimensionality of S action? Exactly, angular momentum, the same as H bar. So H bar, 1 over H bar plays the role similar to that, right? Yeah.
Would it be right at all to think of beta as kind of like almost setting a scale where
Yeah, that's
Hamiltonian is just how many betas?
Exactly. So that's unit is setting the scales. Yeah, that's one way of saying it. Good. Yeah.
The left hand side, like we know it's setting like the Boltzmann constant equal to 1.
Yeah, of course. Yeah. And so you should use because it's 1. One important lesson here is that, so when our fluctuations here are large, what controls the size of fluctuations? Quantum field theory has to do with fluctuations, right? Beta controls the size of fluctuation. Is it beta or what power of beta? Not sorry, what power? Is it beta or is it T? The larger T is, the larger the temperature, the larger the fluctuations, right? The smaller beta, the larger the fluctuations. That analogy, so beta is analogous to 1 over H bar. The smaller the H bar, the larger 1 over H bar, right? That means larger fluctuations. Sorry, the other way around. Sorry, the other way around. Larger the H bar, so H bar is like T. H bar is like T. The larger the H bar, the larger the temperature, the larger the fluctuation. Sorry, I misspoke. All right, good. All right. So here what we have is that minus logarithm of Z of B. This is the background field method. We call it the free energy in the presence of the source as a function of source. And taking derivative with respect to this gives you magnetization. Similarly, we do the same thing here. Good? All right. Now, in StatMech, we all know that there's something called Gibbs free energy, right? And it's now, Gibbs free energy is a function of the magnetization, right? Which f of b plus mb is, you just take the f of b. Notice that f of b has all the quantum effects in it. Has all the thermal fluctuations in it, sorry. Has already taken all the thermal fluctuations into account, right? Del G M del M is B of X. So similarly, in effective action, we make the same Legendre transform, right? Such that del phi classical del phi is J. Now, why is this called effective action? Because action is a function of phi that has only content. The only thing that the action knows is about the classical solutions. effective action is a function of phi that knows about quantum correctness. Good, that's why I call effective action. Good. And we explicitly discuss, and I'm going to review now very briefly, that effective action is the generating functional of 1-pi diagrams. Are there any questions? So how do we see a connection between 1-pi diagrams and effective action? We first start this way. We start by taking we just had this equation, right? That was a defining equation of effective action. Then what you say is that I'm going to take functional derivative from the left side and the right side of del j mu. Good. So this will give me a Dirac delta function. And this I've written over here. Then I put in, so I do this. Or I call this Z, I think, right? Right? That's what I do. Now, the reason I do this is that now it's clear that once I add this term is minus del W del JZ. Sorry, my bad. Phi classical is minus del W del JZ. So this term is another derivative of it, which is the 2-point function connected piece at some finite J. Good. Those are the rules of the game. Good. So then immediately what you learn is that the Dirac delta function is integral over Z of J connected 2-point function, right? Connected 2-point function, the second derivative of gamma. So what did we learn? We learned that the first derivative of gamma, just gonna list it here. It's a functional of the action, where the first derivative gives you J. Good. The second derivative gives you -1 of right? Now, what is the meaning of -1 here? I made an analogy, right? I made an analogy with matrix multiplication. These are kernels, right? These are bilocal kernels. Is that part clear? So to write x and y here is, yeah, you understand. Good. We went through that last time. What was 1 over the 2-point function? So what was the 2-point function in momentum space? Free theory. No, just Fermi. There's no slash. It's not fermions. We're talking scalar. What's the 2-point function scalar field in momentum space? This you know. You should. Sorry. Correct. Yeah, it's an inverse propagator, right? So here the difference is that this is just a for the 2-point function, right? This is just a connected piece, right? All right. Taking derivatives with respect to J, let's take further derivatives. If you want the third derivative, del J of the 2-point function J connected, it's the same thing. Now you're going to insert this again and integral over Y, right? The 2-point function was del 2, the second derivative of effective action -1, right? Del J, and I've inserted the resolution of identity. Good. Now, again, this gives you a 2-point function. I said this before. The rest of that comes from the following identity that you should know as physicists. Oops, minus sign, very important. It's a correct statement for matrices or operators. It's correct for operators, right? This is the original. Good. So what do you learn? There's a diagrammatic way of writing this down. What is this guy connected? How are we drawing this guy connected? Let me draw it for you. So the left-hand side is phi x, phi y, phi z, j connected. Diagrammatically, here's what we draw. Good. X, Y, Z. What is the right-hand side? The right-hand side has, sorry, W. So there, WZX. Okay. WZX. The right-hand side has what? Has W and Y, right, connected this. Good. Then you have what? You have third derivative of gamma, right? Y x and v, right? Y x, no, there shouldn't be any u. There shouldn't be any and v, and then the rest of it is v, z, x, u. If you recall, the finite diagrams, we barely work with them, but when we derive them in real space, when you connect lines like this, you have to integrate over position, right? This we saw from quantum mechanics finite diagrams as well. So these are integrals over y, v, and u. There. So this is the diagrammatics of it. Now, what is this guy? Right? What is the interpretation of something like this? This is a 1 pi 3-point function. Right? Because if it had something that was not 1 pi, it would have been in here. Or here, or here. This is 1 pi. So now, to convince yourself that the fourth derivative of effective action, so you just have to repeat this, to convince yourself that that this is the generating functional for the 1 pi diagrams at higher points, what you have to do is just take yet another derivative. Now you see algorithmically how it works, right? You take 4-point function j connected, you take the derivative, use the same thing, and here's the diagrammatics of what you find. You find the 4-point function, the full thing. Sorry, the 1 pi 4-point function is equal to the fourth derivative of this guy, with these guys connected. But now there is this diagram that pops up. So this is just what you get. What I'm showing you is what you obtain if you just take one more derivative diagrammatically. You get this and the two other channels. Hopefully it's clear what are the two other channels, right? Do I need to draw them? What do I mean by the two other channels? What was this channel? What did we call it if this was the Feynman diagram direction? T channel, if you're going this way, right? So the S channel would be this, right? What's the other one?
Swap to X.
Right. So what happens is that when you repeat this derivation, you're going to get this. Now you stare at this equation, this structure, and you want to interpret what the meaning of the fourth derivative is. It's the 1 pi 4-point function.
So you're saying the fourth derivative itself is the 1 pi or the combination of that?
No, this guy is the 1 pi. This guy. So this is the sorry, I think I misspoke. This is the connected piece. This is the connected piece. Right? All right. And then you could just repeat this and convince yourself that this is the generator. All right, questions. So to summarize, in quantum field theory, here's what we have. You have an action like this. What was this? This was a partition function. But if you want to calculate what was the point of the partition function? One point of the partition function was that if you source it, right, call this z of j, then derivatives of z of j will give you correlation functions. How do I see that? Every time you take a derivative with respect to j, it brings down a phi. Right? So del I phi of x, del k, right? Del I phi x1, x2, del I phi xk z of j is at j equals 0. Let's see this at j equals 0. This is just a full k-point function. But notice that if I calculate this function before setting j equals 0, that function knows about all the correlators. Well, it's a functional. It's a functional of the source. If you take this guy and take similar derivatives, what do you obtain? Connected correlators, otherwise known as cumulants in the StatMech analogy, right? Connected ones. Now, if you take, so W of j, if you take W of j, which is minus I log W, z of j, and add to it, actually there's no I. This, right? What you as a functional of phi, I call this phi class. Okay. As a function of this guy, now this is something that looks like the action. Meaning what? It's a functional of phi, right? I'll say in a second what's the connection, is exact connection actually, but it contains all the data of the quantum thing. In particular, if you take derivatives with respect to derivatives with respect to I, same derivative structure, right? What you obtain is the 1pi answers. Good. Now, of course, this is a function of h bar. So expand in h bar to the 0 order in h bar. That's a classical answer. What do you expect this guy to be to 0th order in h bar? Tree level. So what should it be? It's a function of the field. What function is it? It means what? It means how do you construct it? You start here, right? And you're looking at the lowest order in h bar, right? Where is that? What's that physics? No. No. That's quantum. Vacuum expectation value has quantum. So it's the limit of h bar going to 0. It's a functional of h bar. If I want to see the lowest order, which is h bar to 5, 0, I just send the h bar to 0 limit, right? In that limit, what happens to this path integral?
Goes to some classical.
Exactly. H bar going to 0 limit of this, you get the saddle point approximation, or if there's an I here, they call it what? Stationary phase approximation, which means that this path integral is well approximated to the zeroth order, is equal to what? Extremum of this, which is just achieved. It's just a action, right? So to the lowest order, this guy is the action. You expand it, order by order, it corrects the action in H bar. That's why it's called an effective action. Good. It contains the effect of the H bar corrections. All right. So now, I'm gonna pause here. Are there any questions? I'm gonna change. Let me. I'm gonna change gears and. Are there any questions? Good. So, what are the tools that we have to build quantum field theory? Quantum field theories. What are the tools that we have? You start with, go back to the principles of Landau, right? You first have to pick a Lagrangian, right? Lagrangian, you just pick, a bunch of E-reps of the Poincare group, right? Their classical field content. That gives you an action, expanding derivative and all of that, and you get action, right? Then you just do basic dimension counting to see what is relevant, what is irrelevant, blah, 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 right? So you try to pick something which is renormalizable. Good. And then you want to put that inside the machinery of inside the path integral, right? And calculate. A question. So this effective action, which contains all the correlation functions, right? Order by order in H bar, to the lowest order, it comes out as the action. And then there's an H bar correction, there's an H bar squared correction, there's higher order in H bar, right? What do these terms look like? So you did dimension counting, right? You put certain interactions. Let's say you put lambda phi 4. Could a term here appears as lambda like phi 10? Can it appear here? Sorry? With some coupling. Well, actually, that's a very, very good point. There's some physics associated with it, but tempted to say something about it. Let's say that, yeah, there's a fix for that. There's a fix for that. Could something here appear? Yes, in principle it can. There's one thing that would stop it. The only thing that would stop appearing something crazy here is symmetries. If the action had the symmetry, and this field that we put here of course, this is the measure of the integration as the symmetry forbids those terms. The problem that we're facing in constructing quantum field theory is that, okay, you come up with a candidate for the tree-level action, you put it inside the path integral, hell breaks loose, and you generate quantum corrections, generate the worst case scenario. Anything that's allowed by symmetries will be generated. Anything goes. Because what you put here is bare parameters, right? There's no physics associated with what you put here. We're going to see explicit examples of these higher order terms being generated under, as you look at H bar corrections. And not only they are generated, but also pre-generically, anything, the rule is like this, anything that's not forbidden by symmetries is gonna be there. Right? So what our sort of hope for building a theory that's sensible, has corrections that are tamed, is to just start with something that's very, very simple. So the theme you're gonna see is gonna be the role that the symmetry plays in renormalization. How symmetry makes H-bar corrections tame. Right? We're gonna discuss that connection at the level of renormalized perturbation theory. Good? Today, that's what we're gonna do. Yeah.
It seems like you have to kind of say at the outset that you want these symmetries to be respected at all works.
Yes. So, very good. Very, very good. What is that? So what was a symmetry? It was a transformation of phi that was leaving S phi fixed, invariant. So you're not worried about this guy. What can fail so that what's the only other thing that can fail? So if this is symmetric, if your measure is symmetric, then you're golden. So your symmetry is quantum. Now, the problem, and what we're gonna do is that if you want the classical symmetry to extend to the quantum world, you'll have to pick this to be symmetric as well, the measure. The very notion of anomaly. So far you haven't seen it, but we're gonna come back. You just saw that before. And what was anomaly? Anomaly was a symmetry that you had classically that no regulator could respect. It's equivalent to saying that there is no way of picking a measure that respects the symmetry. Think about it this way. A symmetry that is only a classical symmetry is not the true symmetry. It's an accident. Right? So true symmetries we're interested in are quantum mechanical. We're going to come back to that. So for now, we're going to be dealing with setups where this is nice and symmetric. Okay. All right, very good. Now, let's try to build in just start with scalar field, and let's try to build in some symmetries, right? So if I have a bunch of, say, scalar fields like this, minus half del phi squared, right? And some interaction terms, or some masses, blah, blah, blah. So this theory we analyzed. What I could do is that I could take a whole bunch of these guys. Good. Theories of, and then the question comes up, am I going to couple them? Of course, if you don't couple them, you don't have a new theory. Right, you just have a bunch of copies of them. What you would be interested in building new theories is coupling them, phi 1 to phi 2. Right? Can you come up with an intelligent way of doing that? Using symmetry. Take phi, right, to be a vector. Phi 1, phi n. We did this before. Then write del mu of phi, del mu of phi transpose, minus, say dagger, say these are complex, and then put, I don't know, mass term or contraction terms. Can you see that this results in traction terms between phi 1 to phi n? If you just expand it, you're going to get such things. Of course, if I just put the m squared term, nothing interesting will happen. But interaction, once I include interaction, it will naturally result in interaction between these guys. But now there's a symmetry that restricts this. So I'm gonna walk you through this. All right. One more thing. What are the symmetries of our universe in particle physics? Just space-time symmetries. Yeah. Poincare symmetries. Pick a generator. Give me an example of a generator. Sorry?
Del X.
Del X. Just Del X.
Del.
Translation.
Yeah.
Translation. Okay. Is this room symmetric under translations?
Not really.
It's not. So what are we talking about? But don't say fancy words yet. So what is symmetric? There are two different things. One is your state, whether your state is symmetric. The other one is dynamic, is your Hamiltonian symmetric. Does your Hamiltonian have a symmetry? Right? These are very different things. Now, what is important is that in a lot of systems, if your Hamiltonian has a symmetry, the vacuum, the ground state will have that symmetry as well. Right? Can you argue for it? Can you just give me a basic build up an argument on the fly? What do I need to say? What goes wrong? What goes wrong if I have a symmetry and my vacuum doesn't respect it?
So we have infinite bubbles.
Sorry?
We have infinite energies going down past the vacuum.
No. So the vacuum has energy. All right. You have a Hamiltonian. I think this is an important lesson in physics. You have a Hamiltonian. You have a symmetry, which means that there is a charge that commutes with the Hamiltonian. Good? All right. Ground state is the state that's killed by the Hamiltonian. Good. Has the lowest energy. Actually, I don't even care about killed or not. Right? So to say that the ground state respects the symmetry, what does it mean? It means that it's also killed by Q. Right? Now, this is usually the case when the symmetry is preserved, the vacuum state preserves. But it doesn't have to be. It's possible that this is not equal to 0. But then what happens? Give me an argument. What's the physics of this? If your vacuum is not killed by Q, is not invariant, what happens? No, the symmetry comes from this. The fact that this was our definition. This was our working definitions.
And if you put another Hamiltonian there,
Mm-hmm.
it's not killed, so it's no longer the ground state.
No. You're on the right track, but just write down the algebra. So you're saying that put another H here, right? This vector is not equal to 0. These guys commute. So that you could write it as Q H omega. Actually, no, that was a good one. So it's equal to 0. No, sorry, my bad. You get this. You get this equation. Yeah, this is actually equal to 0. So what did you find?
Another ground state.
Exactly. So it means that if you require that your vacuum is not preserved under the symmetry, the new state you get by acting with the charge on it is a new ground state. So what do you have? You have vacuum degeneracy. So what is the assumption that will kill this setup? Uniqueness of the vacuum. Good? You're with me? An example. Let's just jump into field theory. Scalar field theory. what's a symmetry? Well, let's not worry about the details. What's the symmetry of this action? Yeah, so there's a Z2 symmetry, which is pi going to -5, right? Previously, I used this to conclude that the 1-point function of pi is 0. I was kind of lying. That was assuming that the vacuum state is respecting the symmetry. This is just the action. Good. So the uniqueness of the vacuum, all along I've been saying the vacuum. You didn't ask me which vacuum. Right? Now in physics, in many setups, you might end up with a 1-point function here, depending on your action. I can write down an action, which is actually we'll see in a second, which is Z2 invariant, but you're gonna pick a phi classic. Good. Can you give me a simple example of this? Symmetry breaking. Just with the action I've written. So this clearly has a Z2 action. This is a potential, right? Think in terms of the potential. So as a function of phi, V of phi has a form. What does this look like? If m squared is positive, if lambda is positive, this is something like this. Right? And then the Z2 symmetry will tell you that, well, your ground state better be down here, phi equals 0. Now, how can I cook up a setup where the Z2 symmetry is present, but the ground state is not Z2 symmetry?
Mexican hat.
Well, that's not Mexican hat quite yet, unless your Mexican hat is cut. It's just potential. Right? Now, what are your ground states? These 2 points. Right? Notice that now, are they Z2 symmetric? No. But the action of Z2 takes you from one to the other one. Good? Now, if you take there's another funky thing that happens. If you take the classical action, we've been talking about is extremize on the classical solutions. What are the extrema of this action potential? There are 3 points. So what used to be the vacuum is still a classical solution, but why is it not a ground state? What's special about it?
Unstable.
It's unstable. Exactly. As a matter of fact, yeah. Good. All right. So that's why we're going to be discussing. Now, imagine you have a theory that has a potential like this, right? For example, this room. We're working in this room. There is no translation symmetry. However, because the laws of physics are translation invariance, that tells us a lot about our state, our physics, right? Is it possible that you start with a system like this, right? And symmetries that are not present in your vacuum state, but they're present in your dynamics, teach you about, you get all the benefits of symmetries, right? Even though your vacuum state is not respected. Now, here's some important lesson to be learned. The big statistical physics, right? What was the source of fluctuations? The source of fluctuations were thermal, right? Imagine you have some sort of degeneracy like this. What do fluctuations do? They make you fluctuate, right? You have a vacuum, you pick a vacuum, and you fluctuate, right? As you increase the temperature, the fluctuations get larger and larger. At some point, they become so large that you just roll over, and in the very, very large temperature limit, you basically don't see this at all. That's the statement that this room might not be relativistic invariant, but if we take this room and accelerate it near the speed of light, the collision of this room and another room similar, will be governed effectively by equation, special relativity. So high energies will restore symmetries. The high energy modes respect the symmetries, roughly speaking. Same principle holds for quantum corrections, right? When quantum corrections are large, sorry, no. All right, I send the lesson because I send across a message because I'm not going to talk about quantum yet. I'm going to talk about the StatMech. Are there any questions so far? Oh, I'm really behind. Okay. So the simplest example of spontaneous symmetry breaking is an Ising model. Yeah, Hamiltonian has SI to going to minus SI symmetry, right? That's the Z2 symmetry. But the ground state of Ising model is has spontaneous symmetry breaking, right? All up is one state, all down is the other vacuum. Degenerate vacuum. Good. Magnetization, which is your field, right, is not zero in the vacuum. Good. And Z2 will take one magnetization to the other magnetization, the action of it. So one vacuum to the other vacuum. Now, if you've taken statistical physics, you might have seen this. So, sorry, in this setup, 1 plus 1 dimensional Ising model, 1D Ising model, since that there's no plus 1. The moment you turn on the slightest thermal fluctuations, not at zero temperature, this degeneracy is washed out instantly. So if you take the free energy, instead of taking the ground state, if you take the free energy as a function of fixed beta, and you minimize it, there's only one minimum, and it respects the symmetry. Okay? So thermal fluctuations, no matter how small, will wash out spontaneous symmetry breaking in 1D. Yeah. That's my next point. In 2 dimensions, things are a lot more interesting. Thermal fluctuations, there is a phase transition. Below a phase transition, there's spontaneous symmetry breaking. And then there's a critical temperature. Above that temperature, symmetry is restored. Good? All right. So, yeah. We're going to be studying a similar thing in quantum field theory. So in quantum field theory, this occurs, right? So you could have an action, which is, I wrote here, Z2 symmetric, right? But for example, if I pick this term called mu squared to be negative, right? Then my Lagrangian looks like this. My potential looks like this, right? And it's minimized, and these two minima, which are plus minus square root of 6 over lambda mu. These are the minima. Pay attention to the notation, because this is a notation I'm going to use for Standard Model and Higgs and all of that, right? So V are the expectation values. This is the potential. I'm just drawing the potential. Good? Also recall that the Ising model in the continuum limit, at least in 1D, was nothing but scalar fields here, right? All right, good. So now, here is the funny part. There's an energy barrier here, right? Let's say you're sitting down here. You're stuck in one of these vacua, right? Now you start considering quantum fluctuations here. The very fact that the full theory has the symmetry will put constraints on this low energy theory, even though it's like down here. We're going to see that. And the behavior of this theory is going to be tamed. So a trick that we're going to use is we're going to write down Lagrangians that could come from expanding around a vacuum of a theory that has some symmetry spontaneously broken. Right? This is a sort of unification in Standard Model particle physics. Good. All right, so here's the setup. Everybody is clear what the setup is. So what I'm gonna do is, so the vacuum expectation value is V. I'm gonna take phi of x to be V plus some sigma of x, right? That's I'm gonna take to be small. Good. Now I take phi of x V of plus. I expand the potential. I'm gonna get a constant piece. There is a kinetic term for sigma, right? There is a mass term for sigma. There is a sigma cube and sigma 4 term. Do you see what happened? My theory initially didn't have a cubic term. But in this expansion, I found the cubic term. But there's also something really interesting. So there's one extra coupling, right? Previously, I had only mass, right? I had only mass and the lambda phi 4. That theory had two couplings. But this low energy theory, if I don't know about this UV completion, has more couplings. But the fact that it comes from spontaneous symmetry breaking of another theory says that these coefficients must be related. So now think of it this way. I come to you with some sort of Lagrangian that's like has all sorts of higher order terms. And you look at it and it's like, no way on earth this would be renormalizable or nice. But if this comes from spontaneous symmetry breaking of some theory that is renormalizable, then you're golden. Right? So now put this Lagrangian density inside the action. There will be the constant piece that comes out. Right? And then you're going to look at the fluctuations of sigma e to minus SC. Good? Question so far? So what's going to happen next is we're going to start seeing, going forward, we're going to see all the magical consequences of symmetry. The next example we're going to discuss is exactly the linear sigma model. So I take an ON symmetry, global ON symmetry, right? I take a vector of phi 1 to phi n, right? I put them here, and hopefully you understand the notation. Good? So it has the ON symmetry, meaning that phi A under rotation matrices are orthogonal matrices. Orthogonal means that R transpose R is identity, right? This is a symmetry. The potential takes this form. So, sorry, my bad. So this is say if it's O n is equal to 2, so you have phi 1 and phi 2. These are the rotations. Now, I can tune, by picking this term to be negative, compared to the other one, I get a Mexican hat potential. Good. Now, what are the vacua of this? What are the extrema of this potential? There is a point in the middle, phi equals 0, which is unstable, and then there is a circle worth of it. So there's a continuum of vacuum. What is the physical meaning of that continuum of vacuum? If you have a field, right, that oscillates down here, right? Down here, if I zoom in here, what does the potential look like for this oscillation? That's m squared phi, m for some m squared phi squared, right? So the curvature of this potential is a measure of the mass of this mode. Good? Now, take the Mexican hat potential term. There is a mode that moves you around the circle. What's this mass? 0. So this will be a principle. Classically, you can prove this, that every time you have spontaneous symmetry breaking, there will be a massless mode. Quantum mechanically, there's a Goldstone theorem that guarantees this. And that's where normalization comes in. Right?
And that's general for any dimension.
I'll say in a second, actually. We can make a group theoretic. So what is the vacuum? now there are many vacua. Pick one of them. 0, 0, 0, V. For example, in n equal to, pick this one. And V is mu over square root of lambda. Now, what we're going to do is that we're going to take the fluctuate, we're going to expand around this vacuum. There are the directions of fluctuations which are orthogonal to the direction that we picked, and then there's the direction this way. Hopefully, now expand. So there's n minus 1 directions here, and then 1 direction here, right? One of them has to do with oscillations here, and the other one has to do with orthogonal directions, n minus 1 in orthogonal directions. Take the Lagrangian density and expand it this way in terms of this field. Here's the action you get. You get a constant. So pi are the fluctuations in the perpendicular directions and to the vacuum. It's the thing that takes you from one vacuum to the other vacuum. All right? So here's the kinetic term for pi. Where is the mass term for pi? There is no mass term for pi. There's interaction between pi and sigma, right? Pi and sigma, pi 4, all sorts of terms, but there is no mass term. However, the sigma term has a mass term, which has the right sign, actually. It's massive. It's this way. But notice also now we got all sorts of interactions between these guys. Now, this is an interacting theory that we have a bunch of scalars that are interacting with each other. They're not really scalars, unless this was O2. But if I started by writing this action, in principle, I would have picked all sorts of coefficients here, separate coefficients for each of them. That theory is going to be awfully behaved quantum mechanically. But if you tune these coefficients to this particular form, then the symmetry will protect you. Even though it's spontaneously broken, it will protect you. Good? Here's the gold sum theorem. Spontaneous breakdown of a continuous symmetry implies that there are new massless scalar fields. Every time you have a continuous symmetry, you recall that for every generator, right, you get a charge. I'm correct. So you have these conservation laws. Notice that the conservation law is still correct. The vacuum is not preserved under a symmetry. The theory is still conserved, right? There are conservation laws, dynamics, everything follows the conservation laws. So this is the so-called Nambu-Goldstein boson. Sorry, there is one scalar particle for a scalar massless mode for every unbroken symmetry. Sorry, for every broken symmetry. I misspoke. For every broken symmetry. So if you start with ON, how many generators does ON have? N times n minus 1 over 2. You break it down to ON minus 1. That has n minus 1 times n minus 2 over 2. The number of broken generators is n minus 1. For each broken generator, you get a massless mode. The beauty, and they're called Nambu-Goldstein boson. The beauty of the theorem is that we're gonna very briefly, maybe not today, see that their mass is actually quantum mechanically protected. So classically, at the level of the action, it's massless, but because of the symmetry, quantum mechanically is forbidden for them to get mass. That's good. That's how we end up with a photon that's massless diagrams, quantum mechanically as well. We're going to learn about this later. It's a more complicated version of this. So photon is going to become a Goldstein boson, except that modulo some subtleties. That's gauge theory. This is global symmetries. All right. Questions? I want to say a few things about quantization. Well, actually, I should say things about it. Let me try to run you through this. Here's the action. Good. Lagrangian density. Let's do Feynman diagrams for it. You have sigma, 1 sigma, which is the massive mode here, and then n minus 1 Goldstein boson modes, pi i's. So let's invent a diagram. So here's the diagrammatics of it. This is the massless mode, massive mode. It has mass mu squared. And then here are the massless modes. These are the propagators, right? You get a 3-point function with this coefficient for the vertex of sigma. You get an interaction between two pi's and a sigma. This is it. So you get this diagram, you get this diagram, you get all sorts of interactions, and you get this diagram. Now, let's try to do renormalized perturbation theory. Here's where the magic comes in. What is your act? When we started talking about renormalized perturbation theory, I never mentioned anything about the action, about the state. I just start with the action. And the action is symmetric. So here's the full action, which has the ON symmetry. You introduce a Z for the whole ON field, just one of them. Right? And then there are two couplings. So there are two more. You have only 3 couplings in your counter terms. But how many fields in the low energy do you see? You see N fields. There's a massive mode. There are all sorts of massless modes. So if you didn't know about this high energy behavior, you would have tried to introduce a delta for each of these guys. You would have introduced a Z for each of these guys. And you would have, in general, it would have been hard. You would have found that, oh, at first order and second order, all of a sudden, magically, you're going to get cancellation of divergences. The origin of it is this theory. So we're going to see some interesting, cool consequences of it. So what is the 1-point function of sigma? So what are the counter term diagrams? There's the 1-point function of there's a counter term for the 1-point function of sigma. This is this, and then there are these all sorts of counter terms you obtain. There are more counter terms. These are the counter terms you obtain. Neural perturbation theory. Notice that previously, for each of these counter terms, we had new deltas, but here all these combinations are made out of 3 deltas total. Good. Here are your renormalization conditions. So explain to me what this renormalization condition is. This says that the 1-point function of sigma is 0. Why? Now, what was sigma? Right. So, now what was sigma? I picked a V, a phi, and what did I do? I wrote phi to be the value here, exactly, plus sigma. So around here, the 1-point function of sigma better be 0, right? Because I already shifted it. I already took the shift into account. So that's one condition. What is this condition?
Fix the mass.
This fix a mass for sigma. You observe some mass for the sigma, right? And then this is fix a coupling for the 4-point function. Good. These are the conditions we have. Now let's do one loop renormalization. I'm just going to tell you results. So let's pick this diagram. What are the diagrams that contribute to this one? So let me just, this one. So I'm talking about only this one, okay? There's this at one loop. 1 PI diagrams at one loop. There's this diagram, and then there's this diagram. Good. So then the coefficient of this counter term is tuned to cancel these two. You just do the calculation here. You cancel it with this, right? You have three things to fix. You already fixed one of them, right? Look at your propagator for sigma. Here are the corrections with lots of them. These guys cancel by the virtue of this equation. Do you see it? You have to do the integrals, but that's the fact. Then you have all these guys, right? This is the second condition that will fix one more of these guys. Things are looking bad because you still have to look at the divergences in the propagator of this guy. You have to look at all sorts of other divergences. And you don't have at your disposal new counter terms. But Here's what happens. If you just did this calculation, it magically cancels. Look at Peskin. It does the integral explicitly. To just cancel. Why is this important? Why is this cancellation important? What's the interpretation of this as one loop? Actually, sorry. Here you need to do this first. You still have a third coupling, a third counter term. So this you still fixing, right? What's the interpretation of this?
Self-energy for your.
Correct. Which is what exactly? There are two things that can happen. One is the wave function normalization. The other one is the mass. Mass can't change. What about wave function normalization? You have already fixed it by when you looked at this guy, because this already involved. They have the same z. There's one z to work with, right? This guy cancels. So the cancellation of this is important because this would have been a shift in the mass of the Nambu-Goldstone boson. And this means that at one loop, the Goldstone boson remain massless. Nambu-Goldstone bosons remain massless. In fact, there's a proof of this non-perturbatively. Non-perturbatively, they must remain massless. It's a consequence of the symmetry, even though you might at low energy not see it. They have to be exactly massless. And what happens if you look at so there's a scale, right? So it means that quantum mechanically, the modes that are perpendicular are massless, right? What happens when you go to very high energies? At some point, the symmetry is restored. This mode is no longer relevant. That was just a low energy mode. Same thing happens with nanomolar particle physics. At high enough energy, photon is not the relevant degree of freedom. Photon is a sensible thing at low enough energies. Have you ever heard of cosmic microwave background? What is that? It's the first image of the universe. It's the moment that the universe cooled down, the energy density became so low that photon was a viable degree of freedom that could propagate. Earlier, the temperature was so high, I'm lying a little bit. So at higher temperatures, photons also existed, but they were traveling through a medium that was so dense that they could not freely travel. Right? And you could interpret that as some sort of effective mass for the photon. Anyway, doesn't matter. So what happens is that at low energy enough, photons exist. But if you go to very, very high energy, photon is not the right degree of freedom. We're going to talk about nanomolar particle physics. There's something else. It's another gauge theory. All right. Are there any questions? So this was the first hint at how symmetries could save us. Right? In the presence of spontaneous symmetry breaking, your low energy theory might look ugly. However, magically the coefficients might be related. All right. Yeah.
When you said you tune the parameters coefficients for the Lagrangian, so is this done after like physicists try to do the one loop, two loop computation, and then this is how you can tune the coefficients?
No. So if you don't tune them, the theory is simple. You're going to see that the theory is not going to have tamed quantum fluctuations. It's going to be awful. We're going to see that very soon, right? So when we discuss normalization, here what the symmetry, those values are magical, right? Those are the right values, but there is a symmetry, and that protects these awful quantum fluctuations. You're going to see, we're going to discuss that in detail when we discuss normalization. So here at the moment, this was supposed to just surprise you that, oh, there is such a thing, there's such a possibility. Any other questions? Not, thank you so much. Again, the recording is stopped, so the homework 1 and 2 have been posted last week. Say freely, they're not on Brightspace. You email me the answers on Brightspace, blah, blah, blah. Oh, the recording